a little bit away from how to use Coq for you guys to formalize your research. So I decided instead to develop some new material, and I want to thank Richard Eisenberg for some very helpful assistance with that yesterday afternoon. So in large part due to his efforts, I was able to throw together an illustration of how extraction works in Coq that I think will interest many of you. I certainly found it interesting to go through myself. So I don't know how this is going to go. It's rather raw, but some things are working, and I can show you, and we'll see. Okay, so the basic point that I want to make is that simple extraction from Coq into either ML or Haskell is very, very easy. And I want to show you how to do it because you should feel that you can freely do it all the time, because it really works very well. So sorry, let me plug in. So the basic idea is this. You take any Coq term that isn't in type prop. We'll come back to that in a second. So anything that you've defined in type, you just say extract this, and out comes an ML or Haskell transliteration of that thing. So a few high-level words. Officially, you can extract to OCaml, Haskell, or Scheme. What I've been told is that the Scheme basically doesn't really work. It's of historical interest only. And that people that have tried to do Haskell extraction have been a little less happy with the maturity of the extractor and the amount of fiddling that you have to do to get it to really do what you want. Whereas the ML one is the one that is used more, and it's more mature and more tested and so on. So if you have a choice, if you like both ML and Haskell, choose ML. If you like Haskell, it will still work, but you may expect a little more pain. If you really prefer Scheme, you're on your own. Okay, so the basic function, the basic way things work is you write a bunch of inductive definitions and fixed points in type, and you extract them to, say, ML, where they become a bunch of data type declarations and recursive or sometimes non-recursive functions that work just the same. As you might imagine, there's a certain amount of trickery involved in this. So Coq's type system is much more powerful than ML and Haskell's. So you should expect that there is some, the extractor has to pull the wool over the type checker's eyes a little bit. It has to fool the type checker, and there are mechanisms for doing that in both ML and Haskell. So in ML, it uses something called obj.magic, which has an unreasonably and unsoundly polymorphic type. So you're not getting any benefit, basically, from the ML type checker. But of course, if you trust the extractor, which is not verified, there are people working on that, but at the moment the extractor is a non-verified piece of code. But it's a pretty simple piece of code, and you can audit it yourself and see what it's doing. It's not too hard to understand. So if you trust the extractor, then what you get is a transcription of your program into a mainstream programming language that you can compile with your favorite high-performance compiler, and about which all of the theorems that you've proved are modulo the differences between Coq and ML are theorems about the extracted program, which has not been touched by human hands. So it's in this sense that that you can say that, that program extraction gives you certified ML programs. Now, coming back to type versus prop. The main reason why in Coq there is this distinction between type and prop is in fact extraction. There are some other reasons, but one of the big reasons historically is that the Coq developers have been interested in extraction. And if you write a very complicated program using dependent types in very fancy ways in type and then directly extract it, what you'll get is a very complicated program doing all sorts of manipulations of type level stuff, which actually doesn't have any effect on the final result of the program. So, the Coq designers carefully pulled apart this world of computation, which is type, or sometimes called set, and the world of logic, the world of proof, which is called prop, and designed the extraction facilities so that if you have a program living in type with some bits that come from prop, right? So your program maybe demands that you pass it proofs of various things before it's willing to be well typed. Those proofs, the generation of them and whatever manipulation of them your program does in order to maybe pass appropriate proofs to sub-programs that it needs to call, all of that manipulation completely disappears. So everything to do with prop is simply erased during extraction. Okay, so with that outline, let's look at some simple examples. So here's a really simple example. Let's just look at the evaluator for IMP. So remember yesterday, I think, or 2 days ago, we were talking a little bit about evaluating IMP programs, and I said, well, you can have an evaluation function or you can have an evaluation relation. The evaluation relation is more natural because if you have an evaluation function, you have to pass it fuel and so on and so on. So there is a file, it's called impcevalfun, where just for the sake of writing it out, we do give the fixed point definition. Let's have a quick look at that. So there's various versions of it. The final version that we get to at the end, where is it? Final version at the end is this one. And it has the type, you give it a state, a command, and some fuel, that's the I parameter, and it returns you an optional state. So if the fuel runs out, it returns none, and otherwise it returns some and the final state. And we did a little bit of, if you look at the way the code is written, we did a little bit of hacking with the notation mechanism to implement a kind of pseudo do notation in the Haskell monad sense. So because this option state is effectively an error monad, and you need to do some plumbing with it to write this function in a nice way. So the monadic syntax is a nice way of doing that plumbing. Okay, so here's the step function. Sorry, the evaluator. The step is not step in the sense of small step. It's step in the sense of step indexed. Thinking back to a few minutes ago. So this is the step indexed evaluator, and this is the one that we're going to extract. So what we should get is an ML function that takes a state and a command and a number and returns an optional state. And then we're going to need to do a tiny bit of just wrap a little driver around that pattern matches against the result and prints out the answer. Okay, so going back here, here's how we do it. So we load up the Coq environment with some appropriate definitions, either by just giving them or by importing libraries from elsewhere. And then we say extraction. We give the name of a file to extract into, and we give the function or in general, name of a term to extract. And Coq knows that it should recursively pull in all the other things that this term refers to so that we get a complete ML program. So let's look at that program. So we see that it's really pulled in everything. So it pulled in the definition of the Booleans and the negation function on the Booleans and the numbers and all of the functions on numbers. So there's all of that stuff. And now here are the definitions of the data types for IMP arithmetic and Boolean expressions. And here's the evaluator for the arithmetic expressions, and for the Boolean expressions, here's the abstract syntax of commands. And here is the ceval step function. And you can see it's helpfully inserted a comment showing you the ML type of the extracted thing. Okay, so that's basic extraction. That's it. We could compile this program and run it.
Is that extraction something that was part of the book right now?
Not yet. Okay. So I'm fiddling with some last technical problems that are preventing me from exporting it, but I will do it today if possible.
So that you can run it for programs that need more steps than whatever you might guess?
Yeah, probably. I didn't do that just because I didn't want to bother writing a fixed point version of the small step IMP evaluator. So the way you would do that is you would take the small step version of the semantics, because that's the one where the evaluation function is terminating. So you would take the relational definition, the one that's written down in smallstep.b, and convert it to a fixed point that returns an option, right? Because there are some states that don't step. So you would write a function of type state arrow command, state arrow command arrow command cross state option. That would either say, no, this command is finished, I can't evaluate it anymore, if the command is, for example, skip. Or it would say, here's the next state of the program, and here's the resulting state of the memory. And then, having extracted that, you would write a driver that in ML does the loop that runs it as many times as necessary, because, of course, in ML, you don't know that all functions or all loops have to terminate.
So you will always have more useful output from this program running with a max integer than with a small step evaluator.
Yeah, probably. Right. You can also just use this one and give it a lot of people. Or effectively infinite. Okay, so that was that. We're not quite done yet, and if you really want to use the extraction facility, you will want to do a little more work usually. So, for example, we extracted the Booleans and we extracted the natural numbers, and if we try to actually do much arithmetic with those extracted natural numbers, it's going to be pretty slow because they're represented in unary. So they're represented as gigantic heap structures. So one might think, well, why can't I just extract them to the built-in ML type of numbers? And indeed, you can. So here is a few examples of how to do that. So let's extract, for example, Boolean to the ML Boolean type. And the way you do that is you say how to translate the type, and you say how to translate the constructors. It happens that the names are exactly the same, but of course they need not be. In more interesting cases where the constructors are more interesting, you also need to, so in the Boolean case it did it automatically, but in the case of numbers, for example, you also need to provide a recursor, which corresponds to the induction principle for numbers. And that's a term that, basically you should think about church numerals. So it's a term that you give it something to do, a function to do when the number is 0, and a function to do when the number is non-zero. And, well, you can see how it goes together. You can also extract constants to particular ML terms. So I've extracted plus and multiplication and equality into the appropriate OCaml operators. But it's easy to make a mistake. So last night, I also extracted minus into the ML minus. And then I woke up this morning and said, you know, that wasn't a good idea. You can probably see why, but does somebody want to say? You'll get negative numbers. And you don't want negative numbers in your, you don't want negative numbers showing up in your programs. So the definition of minus that we wrote in terms of unary numbers gets pegged at 0 and doesn't go below. And this one would go below. So it would just be, it would lead to craziness.
Isn't it even worse because the bounded whereas net is not?
It's worse in that way too.
So you need to extract the big int.
You should probably, if you want to be careful about big numbers, you should probably extract the big int.
And also, this syntax is really horribly fragile. If you change the order of the constructor, for example, and then you forget to change this, it will just continue without complaining, as far as I know.
Very true.
And especially in the case of the Boolean string, so you extract true to false and false to true, and who knows what happens.
Buyer beware. Okay, so look at imp2. And just notice that the extracted definitions of Booleans have gone away, and we're just using the built-in ones, similarly with numbers. But minus is still using the correct definition. I could, of course, have written my own correct definition in OCaml and extracted it to that. Okay, so this is nice, but I haven't actually showed you how to run it, so I should do that. By the way, when does this file get generated? Just when you execute this top-level thing. So simply compiling this file with coxy will generate imp2.ml. Okay, so here's a complete example. So we need a way of getting programs into the evaluator. But, oh, I didn't show you this, but I actually have a parser for imp written in Coq. That was a hack by Wilhelm Sjöberg a couple of years ago. So that's a good way of getting programs in. We can just write them in strings in ML and do all the parsing in ML code extracted from Coq. And then we need a way of printing the results. And you know, the state that comes out is just a function from identifiers, which are just numbers, to numbers. And let's just print out the first 4, just to kind of see what's in the memory. Okay, so we need a few more low-level things. And I apologize for showing you this. I think it ought to be possible to do this in a simpler way, but the way that ought to work doesn't, and the Coq Club mailing list has not yet come through for me to tell me how it should be done. So for the moment, I can tell you that this works, but it's a little clunkier than it should be. There should be a better way. So I hope by the time I export this for you, you'll be able to see something nicer. And then I need one more sum bool, which is a variant of Booleans with more proof content on the Coq side, and it should also extract to bool. And now here's what I extract. I extract not only the evaluator, but also the parser and the empty state, which is what I'm going to want to run the program with. Okay, so now we can have a look at the driver. Here's what it looks like. So we need to do a little bit of fussing around with strings because the way extraction of strings works is a little fiddly. ML strings are mutable. So you might or might not think it's a good idea to extract immutable Coq strings into mutable ML strings. I think personally I wouldn't care because ML strings are mutable. Integers have negative ones. So what? I'm not using the mutable part, and I'm not using the negative numbers if I'm careful. So it shouldn't matter. But anyway, the natural correspondence is between Coq strings and lists of ML characters. And so that's what this tweak string stuff is doing. So tweak string takes an ML string and turns it into an ML list of characters in this funny specific format that the extracted code likes. So that's low-level stuff. Test is the interesting part, so let's look at it. So test takes a string, and it first converts it to the appropriate representation and then parses it using the extracted parse function. Parse can, of course, succeed or fail. So if parse returns none, then we print there was a syntax error. If parse returns some, then what it returns is a pair actually of a command and a list of the tokens that it didn't use up. So we just throw those away and extract the command from that pair. Then we run the stepper, not the stepper, excuse me, the evaluator, the hopefully evaluator, the step indexed one, beginning from the empty state, passing it some largish amount of fuel. And if what comes back is none, we say it didn't finish in time. If what comes back is a good state, we print out the first few elements of it. Okay, so now to run it, we just need to compile it. Yes? Let me run it for you, and that may make things clear. So the program I was just showing you was the top-level program that produces this output. So it has this test function, and then it calls the test function several times with some typical imp programs. And for each one, it prints out the appropriate result. Okay, so was that your question, or? Why are we doing that? Well, what we extract from the Coq code is the function that takes a command and a state and produces a final state. A final state is just a function, right? It's a function from locations in memory to their values. So we need to, if we want to actually use it, we need a way of making the result visible. And we do that with an ML function print endline. No, I wrote this. So I wrote the Coq stuff, I extracted it, and then I wrote this small, 60-line file that calls the other one. If you look at the top of this file, you can see it says open imp, that is imp.ml, which is the module that was generated from Coq. And then it uses things like parse and ceval step that it gets from that file.
So was parse a function in Coq, or was that?
Parse is a function defined in Coq.
Okay.
And I can show you that if you like. It's a pretty standard parser. The only thing interesting about it really is that we use the same monadic style to make it look nice, even though it's written in Cox rather limited functional language. So it's a standard kind of parser combinator style parser. Good. So that was our realistic example of extraction. Now I want to show you an unrealistic example of extraction, something that you would probably not ever want to do, but I think it's interesting that it's possible. So yesterday, or the day before yesterday, Amal showed us a logical relations proof that that the single step, the small step evaluation relation of the simply typed lambda calculus is normalizing. So if you think about that, there was a theorem at the end. We can even look at it. There was a theorem at the end that said for all terms and types, if little t has type big T in the empty context, then T halts. That is, if you unwrap the definition of halts, in fact, let's do unwrap the definition of halts. There it is. There exists T prime such that T steps, perhaps using many steps, to T prime, and T prime is a value. Okay, so there's a theorem, normalization, which says every well-typed term halts in this sense. Now, we're working in a constructive logic. So what is the computational content of that theorem? It says, if you give me a proof that this term halts, that is, you give me a proof that this term is well typed, you give me a typing derivation, I will give you a value of this type. What is this type? Well, it's a triple, basically. It's a term T prime, a proof, a derivation that T prime is derivable from T by the step relation, and a proof that T prime is a value. So if you ignore the second and third parts, what it is T prime. It gives you T prime, the value that you get from evaluating T. Okay, so what would happen if we extracted the normalization theorem? Well, okay, so it was actually a trick question. The first order answer is nothing. I get something completely trivial because this theorem is in prop. Right? Because, why? Because halts is, where was the definition of halts? Halts is a prop. Okay, so if I simply extract from this proof, I get something disappointing. But if I'm willing to hack a little, and I have somebody like Richard to help with the hacking, then I can do a little better. So here's what I have to do. I told you before, the basic difference between type and prop is that prop is intended to extract into nothing. So it follows from what I didn't say that pretty much everything you can do in prop, you can also do in type. So the fact that this halts thing is a prop is kind of inessential. I can define a different one that lives in type. To do that, I'm going to have to do a little bit of work because this existential quantifier here is also a prop. It's a thing that lives in prop. I can define a different existential quantifier that lives in type. Oh, but the body of this existential quantifier is a conjunction. That lives in prop. Oh, but I can define another conjunction that lives in type. In fact, I already did that. It's called pairing. So I can take all of these basic definitions. So I need to do this with some of the logical definitions. I also need to do it with the typing relation for the simply typed lambda calculus, right? So the typing relation is an inductively defined relation in prop at the moment. That's the way we defined it. I instead need to turn it into an inductively defined relation in type so that the typing derivations are legitimate data structures that will be extracted into OCaml data structures that can be manipulated by the extracted code. Why do I need that? Look at the type of normalize. So it takes a proof that T is well typed, and internally it uses that proof. It does its work by induction on the proof of well typedness. So this normalization function, in order to do its work, is going to have a typing derivation to work with. Okay, so we need to make sure that the typing derivation is also something in type. In order for that to work, we need a few other things to be in type, like we need the definition of value to be in type, and so on. So the way we did this, Richard and I, was basically just change prop to type in the definition of halts, and then just keep whacking on it, changing more things from prop to type until the whole thing went through. There was a little more difficulty because the tactics of Calc don't treat things exactly the same when they're in type as opposed to in prop, and it's some of the ways that they don't are a little bit silly. For example, when it generates, when you don't give the name of something, you just do intros. If the thing is a type, you typically get, if the thing is a prop, you typically get H, because it's a hypothesis. If you move it to type, what you get is not H, but X, for some reason. So you end up going through and doing a lot of small edits to proofs because the names of variables have changed and things like that. And there are a few places where you can't use some tactic that worked in prop, and you have to use some different, slightly different set of tactics. Is that true, even?
No, I think that those were all missing.
Okay, those are all wrong turns. So basically the same tactics work to build things, to build underlying proof objects that live in type as opposed to in prop. But the details are slightly different. So there's a version of, where is it? There's a version of this file called norm in type. And once this is exported later today, you'll be able to just diff the norm version and the norm in type version to see what the differences are. But basically, let's see. Here's our existential quantifier. So we just copied over the original definition and changed all the props to types, and then recapitulated the definitions based on it. Like the notation and so on. So there was a little bit of low-level fiddling, but it only took a couple of hours. And the result is, let's now go back here. The result is that we can say extraction, normalization, and get an ML normalizer. Now, in order to drive that normalizer, we need a little bit more. So remember, the normalizer takes a typing derivation as input. So we need to get that typing derivation from someplace. And fortunately, we have a type checker. So there's a module someplace. There's a module someplace that shows you how to write a type checker as a fixed point. And we can, of course, extract that and get something that checks types. So look at the type of this, though. Is this exactly what we need? It takes a context. That's all right. We can pass it an empty context. It just returns a type, if it has one. Returns an optional type. But what we need is a typing derivation. So where could we get that from? So Xavier knows, of course. So our first idea was, no, we're programming in a dependently typed language. We can fix this function so that it will return the derivation. And so we tried pretty hard to do that, and we failed. I mean, it is possible. I'm quite certain that it's possible, but it involves really fancy use of dependent pattern matching, and we were not able to get it to work in the time that we had. So we thought, oh, we have to give up. We can't do it. We're going to have to type in these bloody typing derivations by hand, and it's going to be a big pain, and we're only going to be able to do two-line examples. And then later on realized, oh, wait a second. In this file, we proved that the type checker is sound. So here's a theorem. It says if the type checker returns sum of t, then it is mathematically the case that t has type t. Or, computationally, if you give me a proof that the type checker returned sum of something, I can construct you a typing derivation. Okay, good. So let's just extract that. So, we need to do a little work to put it into prop and type instead of prop. But then we just extract it. So we extract normalization, the type checker itself, and the proof that it's sound. And then in the driver program, so here's the norm driver, we just have to paste them together. So how does that work exactly? So we